There is something orbiting near Earth that was never supposed to be there. It moves alongside our planet, and its orbit doesn't behave like an asteroid's. When scientists analyzed the light reflecting off its surface, it didn't match anything we expect to find in near-Earth space. In 2025, China launched a mission directly toward this object, not to observe it from a distance, but to land on it and bring pieces of it back to Earth. What China is about to test could confirm that this object is not an asteroid at all, but a fragment of the moon itself. So today, we're looking at what China found hiding behind the moon. Kamoʻoalewa is small, between 40 and 100 meters across, about the size of a Ferris wheel. It rotates once every 28 minutes, which is incredibly fast for an object of this size. And it never gets closer to Earth than about 9 million miles. That's 38 times the distance from Earth to the moon. To put that in perspective, the moon orbits at roughly 240,000 miles from Earth. Kamoʻoalewa never comes within 1/25th of that distance. And at its farthest point, it can be as far as 25 million miles away. Yet despite that distance, Kamoʻoalewa stays with us. It orbits the Sun in almost perfect synchronization with Earth. Same average distance from the Sun. It's as if this rock is tethered to our planet by invisible threads. This is what astronomers call a quasi-satellite, not gravitationally bound to Earth like the Moon, but locked into a dance with our planet by the Sun's gravity. The Sun is the conductor, Earth is the partner, and Kamoʻoalewa is caught in the middle, following a path that looks circular from our perspective, but is actually deeply complex. Kamoʻoalewa lingers. It's been in this quasi-satellite orbit for about 100 years, and it will stay there for roughly 300 more before drifting into a different configuration called a horseshoe orbit. That transition from horseshoe to quasi-satellite and back again is rare, very rare. Among Earth's known quasi-satellites, Kamoʻoalewa is by far the most stable. Most quasi-satellites stick around for only a few decades before their orbits destabilize and they drift away. Kamoʻoalewa has been doing this dance for a century, and it will keep doing it for centuries more. And that stability is one of the first clues that something unusual is going on. Because stability like this doesn't just happen. It requires very specific initial conditions. The question is, how did Kamoʻoalewa get into this orbit? What set it on this path? Now, Kamoʻoalewa was discovered in April of 2016 by the Pan-STARRS telescope in Hawaii. Pan-STARRS stands for Panoramic Survey Telescope and Rapid Response System. It's designed to scan the night sky looking for moving objects, anything that doesn't stay still relative to the background stars. At the time of discovery, astronomers classified it as just another near-Earth asteroid. Quasi-satellites always draw attention because they're so rare, but in terms of composition, no one thought it was particularly noteworthy. Then, in 2017, a team led by Benjamin Sharkey, a graduate student at the University of Arizona, pointed two powerful telescopes at it: the Large Binocular Telescope on Mount Graham in southern Arizona and the Lowell Discovery Telescope near Flagstaff. They wanted to measure its reflectance spectrum. That's the pattern of light the asteroid reflects back to us. Different minerals absorb and reflect different wavelengths. So by analyzing the spectrum, you can determine composition. Kamoʻoalewa is faint, about 4 million times fainter than the faintest star visible to the naked eye in a dark sky. You need a very large telescope to even see it, and you need high-quality spectrographs to measure its spectrum. Sharkey and his team observed Kamoʻoalewa in April of 2017 during its closest approach to Earth that year. Even then, it was barely bright enough to study. But they got the data. When Sharkey looked at the data, something didn't add up. The spectrum was red, much redder than typical asteroids. And it matched something familiar, something no one expected to see on a near-Earth asteroid. It matched lunar rock. Specifically, it matched samples brought back from the Apollo 14 mission, weathered lunar silicates, the kind of material that sits on the moon's surface, baked by solar wind and micrometeorite bombardment for millions of years. Material that's been exposed to space weathering, which reddens the spectrum and weakens absorption bands. This was unexpected, because near-Earth asteroids are supposed to come from the main asteroid belt. They're supposed to be fragments of the protoplanetary disk that never coalesced into planets. They're supposed to have spectra that match meteorites, stony chondrites, iron-nickel alloys, carbonaceous material. Kamoʻoalewa didn't match any of that. Kamoʻoalewa is made of moon rock. Sharkey and his advisor, Vishnu Reddy, were skeptical. They wanted more data, so they planned follow-up observations in 2019, and then again in 2021, after missing their chance in 2020 due to COVID-related observatory closures. Every observation confirmed the same result. The spectrum matched lunar samples, particularly fine-grained Apollo 14 highland soils. The match was too close to be a coincidence. Now, this was shocking, because if it's true, Kamoʻoalewa would be the first known asteroid in near-Earth space to have originated from the moon. Not from the asteroid belt between Mars and Jupiter, where most near-Earth objects come from, but from our own moon, from a world we've walked on, a world we thought we understood. The implications were profound. If chunks of the moon can be ejected into independent solar orbits, then the population of near-Earth asteroids might include many more lunar fragments than we realized, hidden in plain sight, catalogued as ordinary asteroids, never identified because no one thought to look. But how does a chunk of the moon end up in orbit around the sun? That question brings us to impacts, and to one crater in particular. Most lunar craters are ancient, billions of years old. Their edges have been softened by eons of micrometeorite impacts. Their bright rays of ejected material have darkened over time as they're exposed to solar, wind, and cosmic radiation. The process is called space weathering, and it gradually turns bright, fresh material into darker, redder regolith. But some craters are young, and one of them has become the prime suspect in the mystery of Kamoʻoalewa. It's called Giordano Bruno, a crater on the far side of the moon, just beyond the northeastern limb, named after a 16th century Italian philosopher and mathematician who was burned at the stake for heresy, a fitting name for a crater that might have sent a fragment of the moon into space. Giordano Bruno is 22 kilometers wide, about 14 miles. It's located at coordinates 36 degrees north latitude and 103 degrees east longitude. It lies in an area that's normally hidden from Earth, but during favorable librations, when the moon's slight wobbling motion allows us to peek around the edge, we can just barely see it. When you look at images from the Lunar Reconnaissance Orbiter, Giordano Bruno is striking. Sharp edges, a well-defined rim that rises several kilometers above the surrounding terrain. Bright rays extending hundreds of kilometers across the lunar surface, and a dark halo of impact melt surrounding the crater, all signs of youth. The rays are particularly important. They're made of pulverized rock ejected during the impact. Fresh rays are bright because the material hasn't been space-weathered yet. Over millions of years, they darken. The fact that Giordano Bruno's rays are still so prominent tells us this crater is geologically young. Scientists estimate that Giordano Bruno formed about 10 million years ago. So 4 million years is the current best estimate. On geological timescales, that's practically yesterday. The dinosaurs went extinct 66 million years ago. Modern humans emerged about 300,000 years ago. Giordano Bruno formed somewhere in between. Now here's the key. The size of a crater tells you something about the size of the fragments that were thrown into space during the impact. Bigger craters produce bigger fragments, and fragments the size of Kamoʻoalewa 30 to 60 meters require a crater at least 20 kilometers wide. Why? Because the mechanics of impact cratering follow scaling laws. When an asteroid hit the moon, it transfers energy to the surface. Most of that energy goes into excavating a crater, creating a shockwave, melting rock, and throwing debris into ballistic trajectories. But a small fraction of the energy goes into launching material at very high velocities, escape velocities. And there's one more factor. The moon is in synchronous rotation. It's tidally locked to Earth. The same side always faces Earth, which means the trailing hemisphere has a fixed geographic location. It's always the hemisphere facing away from the direction of the moon's orbit. So if Kamoʻoalewa came from Giordano Bruno, and if Giordano Bruno is on the trailing hemisphere, then the geometry works. And it does. Giordano Bruno is located at 103 degrees east longitude. The trailing hemisphere extends from 90 degrees to 270 degrees. Giordano Bruno is well within that range. So everything lines up. But this is still a hypothesis. Compelling, yes, but still hypothetical. And there's only one way to know for sure. You have to go there. You have to collect samples, and you have to bring them back. That's exactly what China is about to do. On May 28, 2025, a Long March 3B rocket lifted off from the Xichang Satellite Launch Center in southwest China. The launch happened at night. Local time, 1:31 in the morning on May 29th. No live broadcast. Just a brief official announcement afterward from the China National Space Administration. The payload was Tianwen-2, China's second interplanetary mission, a spacecraft designed to push the boundaries of what China has achieved in space. A mission that combines sampling technology from the Chang'e lunar program with the deep space operations of Tianwen-1, which sent an orbiter and rover to Mars in 2021. Tianwen-2 is built to do something no spacecraft has done before. It will visit a near-Earth asteroid, collect samples using two different methods, return those samples to Earth, and then continue on to visit a comet in the asteroid belt. 2 targets, 1 spacecraft. A mission timeline spanning 10 years. From launch in 2025 to final observations at the comet in 2035. The first target is Kamoʻoalewa. The second is 311P, Pan-STARRS, a main belt comet with 6 dust tails. But the headline mission, the one that matters for the lunar hypothesis, the one that will make or break the theory, is Kamoʻoalewa. Tianwen-2 is expected to reach Kamoʻoalewa in July of 2026. The journey from Earth to the asteroid takes about 13 months. During that time, the spacecraft will perform several deep space maneuvers to fine-tune its trajectory. Once it reaches Kamoʻoalewa, the spacecraft will enter orbit. Not a stable orbit, you can't really orbit something with near-zero gravity, but a carefully managed trajectory that keeps the spacecraft hovering near the asteroid. Station keeping, it's called. Tiny thruster firings every few hours to counteract the asteroid's minuscule gravitational pull and the pressure from sunlight hitting the spacecraft. It will spend several months in this configuration, mapping the surface with cameras, measuring the rotation, studying the shape, looking for boulders, craters, slopes, trying to understand what this object actually is. The spacecraft carries several instruments for this phase: a multispectral camera for visible and near-infrared imaging, a thermal emission spectrometer to measure surface temperature and composition, a laser altimeter for high-precision topography, and a magnetometer just in case Kamoʻoalewa has any residual magnetic field from its time as part of the moon. All this data will feed into the selection of a landing site, because the next step is the hard part. Then comes the sampling operation. Now, Kamoʻoalewa rotates once every 28 minutes. That's extremely fast. For comparison, the asteroid Bennu visited by NASA's OSIRIS-REx, rotates once every 4 hours. So China is using two different sampling methods, both tested on Earth, both refined through simulations, but both untried on an asteroid this small and this fast. The first method is called touch and go. The spacecraft descends slowly toward the surface. It extends a robotic arm with a sampling head at the end. The sampling head makes brief contact with the surface, just a few seconds. During that contact, one of two things happens. Either a small explosive charge fires, blasting material into a collection chamber, or a scoop digs into the regolith and pulls up a sample. Then immediately, the spacecraft fires its thrusters and lifts off. The whole operation takes less than 10 seconds. NASA's OSIRIS-REx used this method on Bennu. Japan's Hayabusa and Hayabusa 2 both used it. It's proven. But it has limitations. You can't control exactly how much material you collect. You can't sample from beneath the surface layer. And you only get one chance. If something goes wrong during contact, you can't adjust. You're committed. The second method is new. It's called anchor and attach, and it's never been tried on an asteroid. Here's how it works. The spacecraft descends, just like in touch and go. But instead of just touching the surface briefly, it deploys landing legs. 4 of them. Each leg has a drill at the tip. When the legs make contact with the surface, the drills activate. They bore into the regolith, not deep, just a few centimeters, enough to anchor the spacecraft. Once anchored, the spacecraft is held in place. It can stay there for minutes, even hours if needed. And during that time, a robotic arm with a drill can collect samples from multiple locations. So the plan is to try both methods. Touch and go first, as a backup. Get a sample in the collection chamber, secure it. Then, if conditions allow, try anchor and attach. The goal is to collect about 100 grams of material, roughly 3.5 ounces. That's more than Hayabusa 2 brought back from Ryugu, which was about 5 grams, but less than OSIRIS-REx, which collected roughly 250 grams from Bennu. 100 grams is enough. Enough for multiple analyses, enough for different laboratories, enough to answer the question. Once the samples are secured, Tianwen 2 will leave Kamoʻoalewa in April of 2027. It will depart and begin the long journey back to Earth. The return trajectory is shorter than the outbound leg, only about 7 months, because the spacecraft is coming back, not going out. In November of 2027, as Tianwen 2 approaches Earth, it will release a re-entry capsule. The capsule is small, about 0.5 meters in diameter. It contains the sample container, wrapped in layers of insulation. The capsule will hit the atmosphere at about 12 kilometers per second. That's faster than the Chang'e 5 lunar sample return capsule, which re-entered at about 11 kilometers per second. Faster means higher temperatures, more stress, a more precise trajectory required to avoid burning up or skipping off the atmosphere. The capsule will use a heat shield to survive the initial heating. Then it will deploy parachutes to slow down. And finally, airbags will cushion the landing. If all goes well, the capsule will touch down somewhere in the deserts of northwest China, probably in Inner Mongolia or Xinjiang. Recovery teams will be waiting. They'll secure the capsule, transport it to a clean room, and open it under controlled conditions. The samples will be transported to a laboratory, probably the same facility that analyzed Chang'e 5 and Chang'e 6 lunar samples. And scientists will begin the analysis: spectroscopy, mineralogy, isotope ratios, chemical composition, grain size distribution, space weathering effects. Every test designed to answer one question: is this moon rock? And that analysis will take months, maybe years. Science moves slowly. You don't rush when you only have 100 grams, but eventually the results will come out, and when they do, we'll know. Now, after dropping off the samples, the main Tianwen Two spacecraft won't be done. It will use the close approach to Earth for a gravity assist, a slingshot maneuver. Earth's gravity will bend the spacecraft's trajectory and add velocity, sending it on a new path, a path toward the asteroid belt. The target is 311P Pan-STARRS, and that journey will take about 7 more years. The target is 311P Pan-STARRS, a comet roughly 480 meters wide. It orbits the Sun every 3.2 years, swinging between 1.9 and 2.4 astronomical units from the Sun. What makes 311P unusual is that it behaves like both an asteroid and a comet. It has a stable orbit in the asteroid belt, but it also produces dust tails when it gets close to the Sun. 6 of them. That suggests it has volatiles, water ice, carbon dioxide, or other frozen materials that sublimate when heated. But it's not clear why a main belt object would still have these materials after billions of years. Tianwen 2 will arrive at 311P in 2035. It will spend at least a year studying the comet, measuring the dust, mapping the surface, searching for signs of outgassing, trying to understand how water and organic molecules are distributed in the early solar system. This part of the mission is important for astrobiology, because one of the big questions in planetary science is how Earth got its water. Did it come from comets, from asteroids, from volcanic outgassing? If 311P turns out to have water-rich material, that strengthens the comet hypothesis. And it tells us something about where the building blocks of life might have come from. But that's the future. The immediate story is Kamoʻoalewa. So let's talk about what happens when those samples come back. If the samples match lunar rock, the implications are profound. First, it would confirm that the Moon can eject debris into stable orbits around the Sun. That's not a given. Most lunar ejecta either fall back to the Moon, hit Earth, or escape the Earth-Moon system entirely. Only a tiny fraction, less than 1% in simulations, ends up in quasi-satellite orbits. So Kamoʻoalewa would be proof that this rare pathway exists. And if it happened once, it's probably happened many times. Tianwen 2 is not an isolated mission. It's part of a broader strategy. Since the early 2000s, China has been methodically building its space program, step by step, mission by mission. No dramatic leaps, no unsustainable sprints, just steady progress. The Chang lunar program is a perfect example. Chang 1 and 2 were orbiters. They mapped the Moon. Chang 3 and 4 were landers with rovers. They explored the surface. Chang 5 and 6 were sample return missions. They brought back material from the near side and far side. Each mission built on the last. Each one tested technology for the next. Tianwen 2 follows the same pattern. It uses the sample return techniques developed for Chang 5. It uses the deep space navigation and communication systems tested on the Queqiao relay satellites. It uses the spacecraft design philosophy refined over 2 decades, and it sets the stage for the next step, which is crewed lunar exploration. China has publicly stated its goal to land astronauts on the Moon before 2030. The architecture is already defined. 2 launches of the Long March 10 rocket. One carries the Lanyue lunar lander. The other carries the Mengzhou crew vehicle. They rendezvous in lunar orbit. 2 astronauts transfer to the lander. They descend to the surface. If that timeline holds, China will be the second nation to land humans on the Moon, and the first in over 50 years. But the long-term goal isn't just a landing, it's a permanent presence. The International Lunar Research Station, jointly planned with Russia and other partners, is designed to be operational by 2035. That station would include surface habitats, power systems, mining infrastructure, and potentially a nuclear power plant. It would be a platform for resource extraction, scientific research, and eventually, economic activity. This is the context for Tianwen 2. It's not just about Kamoʻoalewa, it's about demonstrating capability, showing that China can operate at the cutting edge of space exploration. building international partnerships, and positioning itself as a leader in the next phase of human expansion into space. Now, the United States is pursuing a similar goal with the Artemis program. Artemis 2, a crewed lunar flyby, is scheduled for early 2026. Artemis 3, a crewed landing, is planned for mid-2027. But Artemis has faced delays, technical issues, budget constraints. The Starship lunar lander, being developed by SpaceX, won't be ready until at least September 2028, according to internal documents. So the question is no longer if China will land astronauts on the moon. The question is whether they'll do it before the United States. And if they do, the narrative shifts. For over 50 years, the moon has been an American achievement. Apollo 11, Neil Armstrong, one small step. Both China and the United States are focused on the same region of the moon, the South Pole. Why the South Pole? Because there's water ice there, trapped in permanently shadowed craters, protected from the sun's heat for billions of years. Water is the most valuable resource in space. You can split it into hydrogen and oxygen. Hydrogen for fuel, oxygen for breathing. You can use it for radiation shielding, for growing plants, for manufacturing. If you can access lunar water, you can build infrastructure. You can establish a permanent base. You can launch missions deeper into the solar system without having to carry all your propellant from Earth. So the South Pole is strategic. Both nations know it, and both are positioning themselves to get there first. China's Chang'e 7 mission, planned for 2026, will explore the South Pole. It will carry an orbiter, a lander, a rover, and a small flying probe. The goal is to map resources, identify concentrations of water ice, test in-situ resource utilization technologies. Chang'e 8, planned for 2028, will go further. It will test 3D printing using lunar regolith. It will demonstrate construction techniques. It will build a prototype structure using materials found on the moon. These are the precursors to the International Lunar Research Station. They're testing the technologies that will allow permanent habitation. The United States, through the Artemis Accords, is building a coalition of partners. 59 countries have signed on. The Accords establish principles for lunar exploration, transparency, interoperability, safety zones. Those safety zones are important. They allow a country to declare an area around their operations off-limits to others, temporarily, for the duration of the mission. Critics argue that this is a way to claim lunar territory without calling it a claim. Supporters say it's just common sense. You don't want someone landing a rover next to your habitat and kicking up dust that damages your equipment. Either way, it's governance. And governance matters when multiple actors are operating in the same region. China, which has not signed the Artemis Accords, is developing its own framework through the International Lunar Research Station initiative. 17 countries and organizations have joined, 50 research institutions. This is geopolitics in space. Two coalitions, two visions of how the moon should be explored and used, and the outcome of that competition will shape the next century of space activity. But let's bring this back to Kamoʻoalewa, because there's one more part of the story that needs to be told. Over the next decade, we're going to see an explosion of activity in cislunar space. Crewed missions, robotic landers, resource extraction demonstrations, international partnerships. The moon is no longer a destination. It's becoming a platform, a waypoint, a proving ground for deeper exploration. And objects like Kamoʻoalewa are becoming interesting for more than just scientific reasons. They're interesting because they're accessible, close to Earth, easy to reach. If Kamoʻoalewa is a piece of the moon, then other quasi-satellites might be too. And that opens up possibilities for study, for mining, for understanding the history of the Earth-Moon system. China's Tianwen-2 2 mission is testing the technologies that will make those possibilities real. Rendezvous with a small, fast-rotating body, sampling in microgravity, return from deep space. And after Kamoʻoalewa, after 311P, there will be other missions. Tianwen 3 is a Mars sample return mission, planned for 2028. Tianwen 4 will visit Jupiter and Uranus in the 2030s. This is a program built for the long term, built to last, built to demonstrate that China is a space power without equal. But space is not a zero-sum game. What China achieves doesn't diminish what others can do. It expands the frontier, it raises the bar, it pushes everyone forward, and in the end, that's what matters. Not who gets there first, but that we keep going. For now, Kamoʻoalewa continues its silent orbit, spinning every 28 minutes, circling the sun every year. Staying close to Earth, Tianwen 2 is on its way, flying through the void, closing the distance. And in a little over a year, it will arrive. It will map the surface. It will measure the composition. It will touch down briefly, carefully, and collect a fragment of this mysterious object. Then it will bring that fragment home. And when it does, we'll have answers. Maybe we'll confirm that Kamoʻoalewa is a piece of the moon. Maybe we'll discover something unexpected. Maybe we'll find that our theories were wrong all along. That's how science works. You gather evidence, you build models, you test predictions, and you wait for the data. Right now, the data is on its way, so we wait. And we watch, because every answer brings another question. And that's how we move forward.